So as mentioned, my name is Hillel. Thank you so much for having me. And I'm going to be talking to you about formal methods, specifically focused on what we call the two hardest problems in computer science. That is cache invalidation and naming things. So what we're going to be talking about is first what those actually are. What is cache invalidation? What exactly is naming things? How we can solve both of these problems and how we do this in practice. Now, one quick thing before I do begin, I do want to say is that I was sort of invited to talk on this, but didn't have to apply and have the potential to get rejected, which means this talk is wildly experimental. I'm going to be working some material that I've been thinking about a lot, and this is not necessarily a first draft. I've given this a couple of run-throughs on my own, but this is the first time I'm showing some of this material in public, so warned you. So a bit about me before we begin. My name is Hillel. My specialty is what's called formal methods, which is how we write correct, verifiable software. I actually have a book on this coming out I'll mention later, and I'm currently just started looking for clients. You can see that there. I'm going to hide that now because I'm kind of embarrassed about business. I also do a lot of sort of like hobbyist work in software history, like how we got where we are today, both in terms of practice and in terms of languages. And this is something in my own life that's been very exciting, but I recently finished qualification as an EMT. So not certified yet. I'm taking the test in August, but I'm now ostensibly capable of doing anything an EMT is allowed to do. So I can fix some of your bones. Not all of your bones, but some of your bones. Try not to break any bones during this talk. So on with the talk. There are only two hard things in computer science, cache invalidation and naming things. Who here has heard this before? So the sayer of this was Phil Keaton at Netscape in the early days. And it's apocryphal. However, as of last year, his son came out and said that his dad did in fact say it, and we're going to trust his son. So these are now the two hard things in computer science, cache invalidation and naming things. For the first part of this talk, I want to go into detail about each one, what makes them hard, and not just hard, but the only hard things. So first, cache invalidation. What is cache invalidation? What is a cache, first of all? Imagine that you have some client and some server or database, and you're making a read. And imagine that the read is deterministic in that it will always give you the same data back each time, but also highly resource intensive. Maybe you're querying a SQL report, et cetera, or maybe like you're doing a really large big data analysis. Every time you need this data, you're going to make another call to the database, do all of this like intense reading, and waste a lot of resources. So what we like to do is instead put this into a cache, some third-party system that is independent of the database, not necessarily, but also has the data. It caches, et cetera, the data. And the thing about this is that we need some way of filling this cache, right? Here's how it normally works. This is the nice case. We ask the cache, hey, do you have this data? It doesn't. We ask the database, hey, give us this data. Database 5 seconds later finishes the process and gives us back the data. Then we dump it in the cache. And now in the future, when we query the cache, hey, do you have this data? It says, yes, I have this data. And you don't have to hit the database again. This is when everything is working out nicely. Now, cache invalidation is a different problem. What happens if after we put something into the cache, we write to that? Imagine this cache now has value C. Database has C, but we write C prime. Then if I query the database, then if I query the cache, I see that there's a value, so I'm going to use the cache value. I'm not going to hit the database, but I get the wrong value. This is a problem. Can everybody agree this is a problem? At least usually. So this is what we mean by cache invalidation. We need some way to know when the cache is out of date and either nullify it so we can refresh it later or automatically refresh it. Now, I imagine you think that's kind of a tricky problem maybe, but that might not necessarily be the hardest problem in CS. And that's because the actual act of invalidating cache is not a difficult problem. The difficult problem is the fact that the cache needs to be invalidated at all. So here's a very rough state graph, a behavioral graph of a system without a cache. This is essentially the timeline of the database. It starts at value C, and then at some point in this execution, it switches to C prime. Does this make sense to everyone? Now, with a cat, so now what we do is we have essentially two states here, two states of this behavior, one before the change, one after the change. We're going to assume the change is atomic, so that way we don't have to worry about the actual change happening, but this can get more complicated later. That's for just a database. But with a cache, we have this additional period of time where the database and the cache are out of sync. This, then at some point, ideally they reconcile, and they're once again in sync. This is what I like to call sort of the rhombus of death. And the reason why is because we now have a space where if a client tries to get this data, it's going to get the wrong value. We've now created an invalid state, temporary state in our system. This is essentially what's called a concurrency problem, where we have multiple things happening all at the same time without any definite order to them. And this is actually the hard problem. Cache invalidation is hard because it is an example of a concurrent system. What makes concurrent systems hard? Well, here's a question. So with this sort of system, how many different behaviors do you think there are? Like, given just one change to the cache from C to C prime and one client that can make queries, how many different possible state explorations can you see, behaviors? Anybody want to make a guess? So, or at least I'll give you all like some time to sort of think about it in your head. So I see Scott says 3. I'm going to write that down. Again, experimental. 6? 18, yes. Wow, dead on. There are 18 different possible executions that can happen here. And again, we heard 3, we heard 6. How can there be 18? Because a lot of people, when they think about this, they think, what?
Because multiply.
Yeah. Well, because a lot of people sort of see like the basic case of like, yeah, the change happens, the query happens there. Very few people get the case where, oh yeah, a client makes 2 queries, not one, but it makes a query, then it makes a different query. This is a different possible behavior. Or what about the case where a client makes a query, and while it's basically waiting for the query to be processed, the divergence happens. This is a different possible behavior that can easily happen in a concurrent system. Or what happens if, well, they just never reconcile? This is also a very common occasion where just one of those concurrent events that's supposed to happen, that we invalidate the cache, just doesn't happen. This happens all the time, that this doesn't happen. Happens, doesn't happen. And the reason why we have sort of 18 behaviors is because as soon as we start sort of adding this kind of concurrent system, there's many, many, many different things the system can do that aren't intuitively obvious to humans. And we can make this even worse. What happens if we can do 2 writes? Then the rhombus of death turns into this Matryoshka fractal nightmare thing where just the act of writing without any clients already has 4 different things that can happen. 5, I forgot to include the case where they just never reconcile. 6, because I forgot to include the case where they partially reconcile and then fail again. So essentially what happens is that as soon as we add events and we add the ability for things to happen in their own orders, we get what's called the combinatorial explosion. What happens here is that the reason concurrency is hard is because time itself is our enemy. The act of having a sense of time here where things are sort of progressing leads to this case where surprising behaviors, non-intuitive behaviors that we can't normally imagine are commonplace. So does everybody sort of see that this can make concurrency very hard? OK, great. I will admit I cheated a little bit here. So I said that we have a cache invalidation, right? Which cache? Because in a very simple Rails app, there are at least 7 different caches going on here. We've got a third-party service that could be the cache, Redis or Memcache. We have, actually, I just heard somebody say that reading a slide out loud is really lame, so I'm just going to let you see this. There's a lot of caches. And which ones actually matter to our problem, I never actually specified. I never described what we actually cared about, because some of these caches are very serious when it comes to invalidating them, and other ones, like the CPU L1 cache, never going to matter for our web service. But these are all still caches, right? This is the problem of naming things. This is usually when people say this, they mean in terms of labeling things, assigning names to things. That's like saying, OK, yeah, so what is a class? Here is 8 things that we're all going to call classes. But there's another way of looking at this problem, which is, how does the name describe something? How do we mean things? I think this might be a bit of a weird concept, so I'd like to give an example here. Who here knows Java? OK, about half of you know Java. On the next slide, I actually have an example of some wrong Java, and I'm going to ask if any of you can tell me what the error is. So thing is that something like even no Java, you heard that as, do you understand the Java programming language? Whereas I said that to mean, do you understand the Javanese human script? And clearly what's happening here is that no Java doesn't have some sort of objective predefined meaning. It only has a meaning in the context that we need it to. And if you think this is sort of a contrived example, let me do something a little bit more close to home. Who here knows Python? And by Python, I mean this Python. Who here would say they're good at Python? Oh, yeah, yeah, I realize that's a trap question.
I'll jump in.
OK, thank you.
Here I am laying it
Thank you.
down.
So I will be honest, I also think I'm pretty good at Python. I actually just spoke at PyCon about contract systems. Here's a bunch of questions that somebody who's good at Python may be able to answer or may not be able to answer. Because it turns out that when we say good at Python, good there is very, very, very contextual. We usually mean that as to solving the problems that I'm currently having with Python. But there's so many different things you can have as a problem that saying good in the abstract just doesn't carry any sort of meaning. This is a concept known as the language game. And the reason I have this crazy guy in here is because the originator of this idea is this famous philosopher named Ludwig Wittgenstein, who is the only philosopher that pretty much every modern day philosopher agrees was really important in the 20th century. And he wrote this book called Philosophical Investigations, which tries to capture this idea that how we use words and how we define things is essentially a question of how we're using them in what context. And even something as simple as saying, like, are you good at Python? Or do you know Java? Has so many different intersecting contexts of what it can mean that just having that name assigned to it doesn't help us. We have this confusion here where people can see completely different things and have completely different uses with the same sentence in the same seeming context. I mean, it's not just caches. What did I mean by concurrency? What did I mean by right or time or correct? What am I actually trying to do when I say this system is correct or not? So can everybody sort of see here why naming things is a problem? This, just to clarify, the last thing, who here thinks that actually made sense? It wasn't just crazy talk. OK, like I saw one person raise their hand. OK, we're going on with this then. So essentially, we have now this convergence of two problems. How do we work with a concurrent system to understand all of its behaviors? And how do we actually say something about anything, especially concurrent systems? So this brings me into how we do this in practice, which is the next part of my talk, specification. Specification is a description we write of our code that describes both the context we're working in, what we actually are using this code to do, and our intentions of our code. It essentially defines the language game, the valid rules our code is running in, and the actions our code is taking. And this may seem, again, like a very academic abstract concept, but most of you have used specification and specification tooling probably in the past week. And I would like to use that for this next section to build up commonplace specifications and into the more abstract ones I'm going to be talking about in the third part of this talk. So there's really two kinds of specifications here, code and systems. Systems are the really, really powerful stuff, and the stuff I'm personally very excited about. But everybody's used code specs, and barely anybody's used system specs. A code spec is something that describes the intention of your code, whether your code is valid or not. The simplest case would be tests. You write a test that has something it's saying about your code. It doubles a number and has some sort of validation. This is considered the specification of our code, and this is what's called the verification, what actually checks that the spec matches your intention. Now, tests are very, very common as like a specification tool, to the point where even things like our spec, for example, will call tests specifications and your primary spec. But tests are widely used because they're very easy, which means they have some limitations. And I'd like to demonstrate some of these limitations to justify why we might want a more powerful system. So first of all, there's no way to tell whether your test specifications are inconsistent. I can have two contradictory specs here. It doubles number and it adds 2, but accidentally give them the same verification, and this would still pass. And I have no idea whether this spec is wrong or this spec is wrong, because they both can't be right. Or maybe both of them are wrong, and maybe I just wrote a really bad function. So ideally, we'd like to be able to say that at least what we're doing with our specification is incompatible. Second, there's no way to know whether a specification is meaningful or just a mistake. If I write it doubles a number, that could be a typo. Or I could have a domain object in my system called a double. You don't know. What we'd ideally like is to be able to sort of connect our spec to the valid domain of our system, so that way we can actually say, no, I've never defined a double, either define it or change your spec. And finally, because a test is plain English, I can do something like this. That's my spec. Ideally, we'd like to be able to only say sensible things with our specifications. We'd only want to be able to say things that we can reasonably say are true or false, and not just nonsensical. These are sort of three major things we want out of a spec system, and one of the reasons why tests don't really make good specifications. Something that does follow all these rules is what we call formal specification. It defines a very formal set of semantics that you can use to build your specification. In one way, this does limit it, because you can only say things that the system lets you say, but it also makes it possible to say things that are only consistent, only true, only valid. The most famous example of this is type systems. Who here has used something like a functional language like Haskell or SML or F#? Fun fact, I'm kind of a meta-language supremacist, so what we do with a type system is specify what types our functions have. For example, the length function has maps from a string to an integer. This is all Haskell notation, because that's what most of the type researchers use. And what we can essentially do with this is say every function must have a valid set of specifications in terms of types. I cannot write length takes a double because I haven't defined a double type. That's thing one it gives us. Additionally, we get a form of automated verification. We can easily take a typed function and its implementation and see whether or not the implementation matches the type. If I write this, for example, I'm going to get this really long stack trace. And I'm going to have some trouble understanding it, but at least it's there. At least I'm able to automatically verify that my code did not match my specification. But, oh, sorry, do you have a question?
Can I really back about 3 slides?
Boop, boop, boop.
Formal.
Yeah.
For that, formal, so is that embedded in the context? Does that have a meaning within category theory?
Formal specification?
Yeah.
No, it's a mixture of an engineering term and a formal methods term.
Is there a category of formal specification?
Wait, like a type of formal specification that's used in category theory, or we'll talk about this after. How does that sound? Yeah.
That's
Okay.
The answer is either, oh, of course, or no, you're stupid.
Okay.
So you did this, no, you're stupid. That's great. Thank you.
Okay. So I don't know. I've done enough of this that I don't quite know the full space of it. So yeah.
I was a little stupid.
Okay. So so in any case, I'm coming back on track. So the problem with type systems, well, not the problem with type systems, but one of the things I said that formal specifications can only let you say what you can say in them. And one of the consequences of this is that the price of types being so easily verifiable is you can't say very much in their formal spec. For example, if I write this as my implementation, it still matches the specification, even though it's blatantly wrong. This will give the negative length. And what we can do is we can actually empower the type system if we want, making our functions more complicated, but in return getting a little bit closer to our final correctness. For example, this, by sort of only being defined over natural numbers, is a length function that cannot give a negative number. So it is more likely to be correct than this, in that it rules out more cases, but it still doesn't guarantee us full correctness. Now, in formal verification, which is sort of the flip side of formal specification, a very sort of common focus on code specs is what's called dependent types, which let us essentially fully specify programs. This is an example of Idris, which is basically like Haskell's cooler younger brother. And what it does is every sort of vector can be statically at compile time checked for its length. So I can say the length function is going to take in some vector with length len and output len. And now I can always say that this, no matter how it's implemented, will match the specification of what I actually intend with the length function. But that sort of lets us see that we can do really powerful things with a formal specification system. We can prove functions are correct. But that doesn't actually help us with our cache invalidation problem. And the reason why is because code specs are tied to specific code, specific runtime. But something like a cache invalidation is a large-scale system spec. It may involve multiple different code bases. It may involve multiple different clients. And for all you know, it may not even involve computers. If it's a workflow system, maybe you're caching somebody's physical lawyer briefs, in which case that's not something you can cover with code at all. Your code is reacting to the world. And that is not something you can specify in a single code base. Maybe if you had a monolith, you might be able to do this. But again, monoliths are great. What am I saying? Moving on. But essentially, the fundamental thing is that there's a difference between what we want in sort of checking that code is correct and checking that large-scale systems are correct, because the code is only one small part of the large-scale system. So we want some form of system-level specification where we can describe our system in a very compact, tight way and use the specification to check if our other abstract idea of what the system looks like actually matches the original abstract idea of the system. Who here's used UML? OK, UML came out in 1997, unified modeling language. And unified, I forget which one. Unified modeling language. It was essentially attempted to create a single universal set of formalized system-level specifications. You may see some stuff on the whiteboard that looks like this, but UML actually has about 14 different possible diagrams. This is called an interaction diagram. And it specifies, this is actually from the official UML language specification. And this sort of is an example of a person communicating asynchronously with a control panel. The problem with UML as a system-level specification is verification. Because you see here that we have both an abstract idea of a person, but also a class here. And we have some concept of a wrong pin, but also very specific methods the code's calling. And what happens is it straddles this boundary between describing some abstract system, idealized system, and describing our nitty-gritty code. And one of the consequences of that is that it doesn't actually easily amend itself to being formally checked. There's a few other problems, but that's the main one here. And this sort of makes it really unsuitable for cache invalidation problems. We can write something, but it's going to so heavily mix our code and our spec that it's just not going to work out very much. So that brings us to the third part of this talk, which is an actual system-level specification language that can actually solve this problem for us. This is called TLA Plus, the temporal logic of actions. This was invented by the student named Leslie Lamport, who is fundamental to both the fields of distributed systems, formal logic, and LaTeX. He invented LaTeX. And his idea was that we can specify blueprints of code instead of code itself. For example, if I had an elevator, I could say that it may go up one floor, it may stay at the same floor, it may go down a floor. Essentially, there is all possible evolutions from every possible state is embedded in the system. Then we can look at that as a holistic set of timelines and see if any of them match our expectations. Did that make sense to anybody? I hope it didn't. Because if it did make sense to you, you probably already know this talk by heart. So it doesn't make sense because this is something that I think is honestly much easier to show than to explain. So for this next part, I want to go through our cache invalidation problem using TLA Plus to show how it can find the issues. We note that one of the consequences, though, of system-level specs is that they look very different from code specs and very different from code. And a lot of people often struggle at the very beginning with wrapping their mind around sort of the new syntax. So I'm going to cheat and use a language that was built on top of TLA Plus called PlusCal, which is essentially all of the same features and functionality, but wrapped around a algo-like imperative shell. This is to make it easier for programmers to start with it.
LaTeX is built on top of tech.
Exactly. If the recording was that LaTeX built on top of tech, that was the thing that somebody said. Actually, question, can you hear? Are you recording the audience too?
No.
OK.
Well, through your mic, yes.
OK. So for the people who are listening to this afterwards, I asked if we can record, if this recording the audience, and the answer is no, except secondhand. Going on. So let's actually now walk through what this looks like as a PlusCal spec and show what the issues we run into are. First of all, we need some variables. I'll say the database starts at some string d1, and the cache starts at some null value. Simple. Now I define a client. The client has some result, and what it does is it keeps looping through this, checking if the cache is null, and if it's not null, it reads from the database and puts it into the cache. And if it isn't null, it just reads from the cache. Everybody follow this. So now I have some system. I now have some formal spec of what the system can do. I can now do what's called a model check on it. The tool we have is called TLC, which stands for redacted, redacted, redacted. Nobody actually knows. And long story. So and what it does is it sort of goes through all possible orderings of what can happen. In this case, only one thing can happen. Client happens, read from DB happens, write to cache happens, client happens, read from cache happens. So what I can do now is put this into the IDE, the TLA toolbox, and run this as an actual model check. This is what it looks like. I had a note here that I missed saying drink water when this starts, but so first of all, you might have noticed a couple things. One, that took a while. This is a brute force solver. It's looking at every possible state. The second thing you might notice is that nothing happened. It output that there was some time, diameter, states found, distinct states, queue size, bunch of like debugging information, and that's it. This means our spec is fine. We didn't actually say it did anything, though. Now we actually have to express our intentions. Here's one intention. Eventually, the cache should match the database. Does everybody see that as one of the possible intentions? Because you're reading from, you're doing a read, you get the cache, you get the database, and you put it into the cache. This diamond there is the eventually operator. It says that at some point in the future, for every timeline, this must be true. So who here thinks that that this is correct? I mean, I'm sure most of you don't because like I'm leading you in this question. So let's now run this. That time I read in advance. So now this thing popped up. This said that it was able to find out that we're wrong. This is actually broken. We cannot guarantee in our existing spec that we will always eventually sync the cache in the database. It also gives us this thing called the error trace, which shows starting from the very initial possible states, and there can be as many as we want initial states, everything that has to happen that leads to this breaking. This is sort of a zoomed in, so you can see first it goes to read from DB, and then it gets the result, and then it does this thing called stutter. We never actually said our client could not crash partway through. That's what stuttering means. We just keep going, and then we just stop, and then we just say nothing ever happens again. And it turns out that if our client crashes, we're never going to write to the cache. Isn't that right? So we have to actually be very explicit with TLA Plus and say, for this particular problem, the client cannot crash. The client cannot stall out. It is what's called fair. Fair meaning it will always get a chance to run. And this may not be something we can always justify, especially at like lower levels. But at a high level, for what we're doing, it's fine. So now if I run this, what will happen? It'll be a success. OK, so that's very simple. You can see how it already sort of was able to see a very, very simple system with just reading and say, no, one of your assumptions is wrong. Now let's add a writing. This is now two things. Either we can read the read stuff, or we have this write thing. And this uses semantics that are actually impossible in most programming languages. First, we've got this either or. And what this does is it says to TLC, hey, you're allowed to branch here. You can either choose a read from DB as your next thing, or you can choose write. And what happens now is that every time we hit this, TLC is able to split the model into two separate timelines and check both of them. If it sees this 4 times, we'll have 16 different timelines. We also have this with DN data. And what that does is it says, at this point, just choose any value in this set that you want and just run with it. Here I define data to be just the strings D1 and D2. So every time we hit write, we have 2 separate timelines. One where we do this where we do this with D1, and one where we do this with D2. OK. And what we're doing with this now is we're just setting the database to equal that, and we're setting the result to match the database, because we can guarantee that those are the same right now. Is this correct? Good point. Metagaming this, I see. No, this is not correct. And the reason why is because we never actually specified that it couldn't just write forever. What it's doing here is it's doing a loop. It is first writing a value, and then finishing, and then writing a value, and then finishing, and then writing a value, and then finishing. It never reads. So we didn't actually sort of specify that it has to both read and write. It can just do one or the other and just never do the other one. And this may seem a bit crazy, but it is a valid failure state. So the solution I have here is to say that this is only allowed to write when you already have the result from the database. So is this correct? Yes. So now let's add another property. Can we always guarantee that eventually the cache is invalidated? And what I mean by this is that if the DB and the cache are out of sync, at some point in the future, the cache is null. And this is essentially the same as sort of the eventually operator, except it only kicks in if this ever is true. So if this is true for one state, for some future state, this must be true. Does everybody follow that? Is this correct? I mean, it's pretty obviously been alternating correct, incorrect at this point, so this is obviously incorrect. And the reason why is because we never actually defined a cache invalidation mechanism. Yeah, we just left that out. So let's define one. And we just have this just as another process that it just forever keeps looping. That just sets the cache to null. And with this, we're correct again. OK, next question. Can we always guarantee that if we read a result from the database, it's correct? This is the final temporal operator. It's the always operator. And this says that this must be true in every possible reachable state. Then we also have this, which is OR. It's the set logic OR. It's not like a V. So is this correct? I mean, again, no. But does anybody see why this is incorrect? Rhombus of death. What we can have is that the client can basically do a write, that's this stuff. And then before the cache invalidator can actually invalidate the cache, however it works, we're just looking at high level, it's just invalidating the cache, we read again. We get the wrong answer. So we can sort of see here how all the really simple issues that we raised as the cache invalidation, all these are now coming up. This is able to find all of these possible problems. And now this is basically the simple case, but I want to actually push this one step further. What if we came up with a brute force solution to this, where the client, after it does a write, will always wait for the cache to be null. It will keep querying the cache, wait for it to be null before it's allowed to do another read. Will this be correct? Does everybody understand what I'm saying right now with this new system? I'm seeing some confused faces. So the new behavior that we're doing, our sort of nuclear option behavior, is that if the client writes, it has to wait for the cache invalidator to run by just, I don't know, a heartbeat or something before it's allowed to do another read. Is this correct?
As long as there's only one client still reading.
Reading ahead, I see. It's correct for one client. What about with two clients? Just by sort of switching this client to, instead of just being something like string to in a set of values, we now have two processes, two clients running simultaneously. We have to adjust our correct read invariant a little bit. Basically, this is just the for all symbol. And now it basically finds a race condition where it says, oh yeah, if one of them is waiting for it to invalidate, the other one can still read. And when we basically add this, we've now made the system so much more complicated that there's actually 130 different possible behaviors that can emanate from this. Because the moment you add multiple systems or concurrent objects, things get really complicated really fast, which is why we need to check them. So you can clearly see that this works for a toy example. Does it work for actual real-life examples? And this is actually a really important question because this has been one of the big banes of formal methods as a field. A lot of things work really well in academia, but don't leak out into industry very much. So with TLA Plus in particular, there are three groups, I'd say, that have had really successful public results. One is Microsoft. One is Amazon. Both of those have about, I don't know, maybe about 5,000 DevOps interns a year. So that basically suggests that this works for a really big company with a lot of resources. The third company it works for was a company called eSpark. Have any of you heard of that company? Well, you don't count. He's heard a different talk I've given. So the reason why I haven't heard of eSpark is because eSpark has 8 engineers. It was my last company. We made iPad apps for schools. We were so far removed from large-scale work. We were very far removed from any sort of embedded hardware or safety-critical stuff. We did an iPad app for schools. But it turns out that because of Apple's wonky permissions and how MDMs work, mobile device managers, this kind of accidentally became a distributed system. And when you have 3 or 4 engineers working on a distributed system who are all full-stack web devs, things get very broken very fast. I actually did an estimation on this where for every new feature we rolled out, where a feature was something that took at least a month to develop, we would have at least one, most often two, critical fires, where we basically drop everything and spend several engineering weeks fixing things in a panic afterwards. Then we decided to use TLA Plus. It was able to find such complicated errors with so many different possible steps that after we started using TLA Plus, instead of having about 1 to 2 critical fires per feature, we had 0. And again, I do need to emphasize, this is an app company who's doing consumer product apps outside of any of the conventional fields where formal methods is known to be useful. And we still found incredible value from it. And this is like not just TLA Plus. Like we're clearly working in distributed or concurrent system, but TLA Plus isn't the only formal specification language. Last thing I want to talk about is a couple of the other ones that are also very powerful and have seen huge success outside of academia. The first is Alloy. Alloy is, just as like TLA Plus is designed around like temporal logic, Alloy is designed around something called relational logic. It is all about modeling relational data, like SQL constraints, graph systems. It was used to actually break several fundamental like internet protocols back in 2005. And I'm currently actually using it to specify package management software. I'm currently working on a sort of a side project of, first of all, like working on the Nix like purely functional package manager, specifying in this. And I've also been working on the new Vigo like MVS. And this is actually, again, a little bit of a weird notation, but it's able to find very complicated bugs in like data systems and any sort of thing that revolves data structures. It's also able to generate pretty pictures for you. It's got a much friendlier UI than most formal methods. The guy who does it is very, very into UI and like UI research. And another one that's also very, very powerful is Harel Statecharts, which is essentially nested state machines that are very good to study UIs. I can sort of specify what any UI can do, how it interacts with like the larger system, and see if that UI is consistent. So to wrap this up, cache invalidation is hard, naming things is hard, specification is good, TLA Plus is good, reading things off the slide is bad. So I'd like to briefly end by just talking about if this stuff interests you, where you can learn more about it. So the first thing is that for TLA Plus, I created a site called learntla.com, which is a very beginner level introduction that uses PlusCal and has lots of exercises and is basically now considered one of the best ways for people to start learning TLA Plus. Leslie Lamport also has a free book online called Specifying Systems, which is the canonical text and heavily covers the theory. He also has a video series that I forgot to put a slide on here, but if you Google TLA Plus video series, you'll get him. He has a lot of different hats. And finally, I'm working on a new book called Practical TLA Plus, which is essentially going to be with APRESS, estimated September 2018, and is going to have a lot of really heavily worked examples, such as building MapReduce, Decker's algorithm, specifying like business features like libraries. But when I say libraries, I mean like reserving books from a library. And that's going to be, talk to me afterwards if you're interested in this. For Alloy and Statecharts, you can find information about them here, alloytools.org and sketch.systems. And that's pretty much all I had to say. I'm of course going to be available for the next 5 hours for questions anybody has. But otherwise, my name is Hillel Wayne, and thank you for listening to my very highly experimental, very rough draft talk. Thank you.